This research paper introduces a novel approach to transferring poses from a reference avatar onto stylized 3D characters, eliminating the need for manual rigging or explicit correspondences. The proposed model combines learning-based methods and classical mesh deformation techniques, allowing for zero-shot pose transfer between significantly different shapes. It utilizes a correspondence-aware shape understanding module to predict part segmentation labels and represent the shape of a 3D character as a latent shapecode. The method also includes an implicit pose deformation module that deforms individual surface points guided by a target pose code sampled from a prior pose latent space. To encourage realistic deformation and generalize to rare poses, the authors propose a volume-based test time training procedure. The paper highlights the limitations of existing learning-based methods and emphasizes the importance of local deformations for achieving better generalization to stylized characters. The research paper discusses a novel approach to transfer poses from various modalities to an unrigged stylized character without additional effort. The pose deformation module learns a neural implicit function that takes the sampled pose code, the learned shape code, and a query point around the character's surface as inputs and outputs the offset of the query point in 3D space. The module is trained with densely annotated human mesh datasets and uses the ground truth offset as supervision. The training objective is defined as the Euclidean distance between the predicted offset and the ground truth offset. The paper also proposes volume-based test time training to address surface distortion and long-tail pose distribution issues. This involves fine-tuning the pose deformation module on unseen stylized characters and applying a volume-preserving constraint. The method is evaluated on various datasets, including MGN and Mixamo, showing improved pose transfer error and character smoothness compared to baseline methods. The paper discusses the data curation procedure for the Mixamo and MGN datasets, providing implementation details of the proposed method and baseline methods such as NBS and SPT. For data curation, the authors follow instructions in 37 to download testing data from the Mixamo website. 1. Focusing on 19 stylized characters and randomly picking one motion sequence for each character. For the MGN dataset, they use the last 16 clothed human characters and sample 200 poses unseen during training to obtain ground truth deformed characters using the multi-garment net. 11. The proposed method's implementation involves computing occupancy with virtual laser scans and optimizing the shapecode with a batch size of 2000, taking an average of 3.41 seconds. The detailed test time training (TTT) procedure is outlined, which involves fine-tuning the pose module to perform two tasks: deforming the stylized character to the target pose while being constrained by the self-supervised volume-preserving loss LV, and deforming the source human character in T-pose to the target pose, supervised by the ground truth human character in the target pose, LDR. TTT is efficient, requiring only 20 iterations in 18 milliseconds without batching, and can be sped up to 12 milliseconds with a batch size of 8. The baseline methods, NBS, 35, and SPT, 37, are evaluated using their publicly available code and pre-trained models. For SPT, the authors train and evaluate the model on the dataset discussed in Sec.4.1 in the main paper, utilizing the small model, 70, to produce motion pairs and supervise SPT with ground truth skinning weights from small. The paper also includes more visualizations, including qualitative comparisons, Fig. 9, deformation results for both human-like, Fig. 10 and Fig. 11, and quadrupedal characters, Fig. 12, and limitations of the proposed method. The authors acknowledge that modeling other categories whose poses are not well studied remains difficult and that their method is unable to solve the articulation of hands, treating them as rigid parts. The research presented on pages 11 and 12 focuses on the evaluation of pose transfer techniques from in the wild videos to stylized characters. The authors compare their method with existing approaches, such as target source NBS, 35, and SPT, 37, showcasing improved results through qualitative comparisons in Figure 9 on Mixamo, 1. This improvement is attributed to the novel pose transfer algorithm developed. The algorithm's effectiveness is further demonstrated by transferring poses from in the wild videos to stylized characters, as depicted in Figure 10. The results highlight the potential of the proposed method in enhancing the realism of character animations. The study also discusses limitations and future work, emphasizing the need for more diverse and challenging datasets to further improve the accuracy of pose transfer. The research paper explores the transfer of poses from in the wild videos to stylized characters, encompassing both human and animal subjects. The approach is demonstrated for human characters on page 13, as seen in Figure 11, where it captures and adapts poses from real-world videos to fit stylized human characters while preserving natural dynamics of human movement. Pages 15 and 16 detail the references cited in the research, focusing on motion retargeting, 3D human reconstruction, and shape deformation. Cited papers delve into various methods for motion retargeting, including skeleton-aware networks, physics-based motion retargeting, and animation setup transfer. Other papers focus on learning implicit functions for 3D shape modeling, such as neural Jacobian fields, implicit function learning, and spatial deformation transfer. Additionally, papers on 3D human reconstruction are cited, covering methods like combining implicit function learning and parametric models, learning 3D dense correspondence, and 3D human pose and shape estimation. Shape deformation is also explored, with automatic unpaired shape deformation transfer, learning shape templates with structured implicit functions, and local implicit grid representations for 3D scenes. Papers on motion editing, 3D character animation, and other topics like learning compositional representation for 4D captures with neural ODE, graph convolutional networks, and neural parametric models for 3D deformable shapes are also referenced. Overall, the cited papers provide a comprehensive overview of recent advances in motion retargeting, 3D human reconstruction, shape deformation, and character animation, showcasing the breadth of research in these areas and the paper's reliance on cutting-edge methodologies and techniques. The research on pages 17 to 18 delves into various facets of computer vision and machine learning, notably in motion retargeting, shape matching, and 3D deformations. The authors introduce novel methods for enhancing generalization under distribution shifts, implicit field supervision for robust non-rigid shape matching, and physically based motion retargeting filters. They also explore neural kinematic networks for unsupervised motion retargeting and spatially adaptive instance normalization for neural pose transfer. Furthermore, the pages cover neural rigging for articulated characters, predicting animation skeletons, and detail preserving 3D deformations using neural cages. These methodologies employ algorithms and mathematical concepts such as self-supervision, implicit field supervision, and physically based models. The findings and novel ideas presented in these pages significantly contribute to the advancement of computer vision and machine learning in areas like motion retargeting, shape matching, and 3D deformations.